Today we're going to have a highly technical presentation, as was said by Szymon. And Szymon and I go way, way back. We've known each other for minutes, really. So I hope that you can enjoy it. I noticed that all of you are C++ developers, so that means you have a lot of questions, I'm sure of it. So please feel free to pick his brain, take as much as you can, and question it, okay? Thank you, and let's get started. So welcome, Szymon.
Hello, everyone. Good to see you here. So my name is Szymon Gutaj, and I'm the guy who's going to talk to you for the next couple of minutes, hopefully about something interesting and perhaps practical. And we are going to talk about C++ template metaprogramming. Oh, even the name is a little bit too long. We'll try to keep the presentation practical, but perhaps not too practical, not to fall asleep, right? Oh, it works. So here's the plan for today. We'll start with the introduction. We'll try to keep it as short as possible. Then we'll proceed to the code. And then we'll have some time for questions and answers, and hopefully for a little discussion. So what is this whole metaprogramming thing all about? How does it differ from, let's say, classic use of templates? Well, probably the definition is quite difficult. I would say that a metaprogram doesn't necessarily have to generate a single byte of code. That's probably the slight difference. And it also does something during compilation phase. We'll talk about it in a second. Oh, sorry. Okay, I was trying to come up with a definition. The best thing I could come up with was that metaprogramming was shifting complexity from the user to the machine, basically to the compiler or to the library, so that you don't have to write all the code yourself. You write a little metaprogram, right? And then it does plenty of stuff for you. One of my very close friends came up with another very nice definition, that is, it boils down to augmenting the compiler, right? Okay, so what are we trying to achieve and what can we gain using metaprogramming? One of those things is correctness. If any of you has ever had to write in a classroom back in the school days, like something like, I will be humble to my teacher 1,000 times, knows that probably it's much better to do it with a script. At least once we learn programming, it's much less error prone, right? We can write some metaprogram, test it, and then it will always work according to the rules which are embedded in it. It also allows us to introspect and check the code at compile time, so that it can detect that the user is abusing something that we didn't intend to happen. As well, we can create libraries or some code, well, not client code, but something like a utility code, which is smarter than the user. It hides all the details. And that's something really good, because then the user can concentrate on the business logic, on writing the software, not on the details. And of course, we are avoiding repetition. Templates allow for, well, not repeating yourself. Metaprogramming brings it even further. We can also gain performance. Well, the most obvious thing is performing things during compilation time, pre-calculating stuff. Any of you who has ever tried going hiking knows that it's probably better to, well, bring your own food with you instead of, well, hunting in the forest for food. So yeah, it may speed up some things. We can also generate fine-tuned code in particular situations. So the metaprogram is a script which recognizes what you're trying to do, and then it applies the optimal solution. And we can also perform optimizations which are cumbersome to handcraft. Right? There are plenty of those places where the gain is very small, there are many of those places. Probably the user, well, it's too much for the user to do it manually. But the metaprogram can do the cumbersome thing for you. And since you are using this code in many places, then the benefit might be substantial. Also, portability. Right? We can automatically adapt to current hardware. We can pick different pieces of code. And what's best is that, we could achieve similar things with a C preprocessor. We could achieve something with some build system tricks. But the good thing is that by metaprogramming, we keep all the code in the C++ realm, which means that, the code is not as dead as it would otherwise be. It's always being compiled, at least. And yeah, the good thing is that we are using one tool. We can also achieve expressive interfaces. Anyone who has seen the C++11 standard library or Boost or something knows that in some of those libraries there's heavy metaprogramming under the hood, but the interface is actually quite nice. Perhaps we'll demonstrate it in further code. We can also create domain-specific languages. So we create a solution, a library, or a utility, which fits exactly the thing that we are trying to achieve. Okay, treat this with a little sense of humor. Basically, I noticed that if you commit some metaprogrammed code and nothing happens, there's a huge probability that nobody has seen it. Probably the reasons are that, there are two kinds of reactions. One reaction, usually extreme. One of them is like, oh, cool, I haven't seen anything like this. Cool, so many angle brackets, wow, what does it do, right? And the second one is like, oh, you could do it in a much simpler way. And I would say that usually those negative reactions come from the fact that metaprogramming is new, right? And that's it. But it's becoming mainstream, so probably many people who don't like it will at least have to get used to it. Okay, the real consequences are that, the development time of your utility code, like the library or the whole thing that you shifted towards the library, depends on your skill. If you're skilled at metaprogramming, that's no more difficult than writing regular code. And also depends on the tools you use. A good modern compiler with good messages, one which is conformant to the standard. There are also tools for debugging metaprograms. I'll mention that in a second. Then comes the maintenance cost. Obviously that requires some skill. Metaprogramming usually touches aspects of the language which are not trivial. So that's the cost. But your user code becomes much higher level. It becomes smaller, more declarative. And that's a good thing because it doesn't clutter the business logic with all of those low-level details, which you usually don't want to mix with the business logic. And also, there's one quite trivial thing, but I guess worth mentioning, is that changes to your library, both bug fixes and new features, propagate to all places of usage. So it also affects your maintenance costs. Instead of changing 1,000 places, you change just one place, perhaps two places, and voila, it works. Okay, there are a few approaches to metaprogramming. You can mix all of them together. The first one is handcrafted metaprogramming, so you basically have the bare compiler, you do all the thing yourself. Then you try to use some prepackaged libraries like the type traits library in STL or Boost, or some, domain-specific or higher-level libraries, but it's up to the thing you're trying to achieve. So, yeah, probably most of you know that metaprogramming was discovered by accident. I guess it happened in some dark basement, smoke flying around, and then those guys discovered that, oh gosh, that's a separate functional language, which is Turing complete. Yeah, and it is purely functional, which means that we've got no mutation. We have to create copies if you want to modify something. We cannot iterate, we need to use recursion. And we measure computational complexity, well, in general case, by the amount of template instantiations. Yeah, we'll show some code, what it means. Okay, sorry for that. I guess that applies to every kind of software engineering, but it has some special place in my heart also. It's quite important in metaprogramming to keep your code orthogonal, which means that one thing should do one thing, right? Do not bloat your classes or your elements of your code with more than one functionality per entity. Yeah, well, you might have one brush at home for both, for cleaning your dishes and cleaning your bathroom, but you probably want to have two separate brushes. Same applies here. You don't want to mix those two things. Yeah. In metaprogramming, conventions are a sacred thing. Pay attention to keeping them. There's already a convention established by some libraries. Good to keep that. Good to stick to that. And usually when you're trying to solve something and you cannot come up with a solution, it means that if you add one level of indirection, it becomes possible to solve it. We'll also show it in the code. Okay, so now the practical part. Let's show some techniques. Yeah, so if any of you sees code which is not necessarily the best industrial practice, please don't throw anything at this stage. Yeah, examples are meant to be fun and easy, not necessarily the best solution in a particular situation. Okay, hello world. We can see three things here. In line number 2, we've got a template which takes one parameter and it defines one nested type def in line number 5. In line number 9, we've got a definition of a class. That's an arbitrary data we are going to use. And then we've got usage in line number 14. And try to guess what the type of hello world is. Hello world variable. Well, yes, it's hello world. Can we see what happened here? The parameter t got forwarded to type, and that's the type we extract from the template instantiation, right? So, yeah. We can operate on types, where the template name is the operation name. In that case, it was this return as is thingy. Template parameters are the arguments, and the nested definition name type is the result. And we've just described a metafunction. So it's a function which, well, happens to be called during compilation time. One small remark. We use the struct keyword here in order not to clutter the code. Usually the access specifier doesn't matter because all the data are immutable, so we don't care, right? And then we can save some typing, and yeah, the syntactical noise is much smaller. One more example. This metafunction adds a pointer to its arguments, right? So the t gets eaten by add pointer, and this little asterisk is being added. And yeah, in line number 9, we can see that if we provide it with int, then the result is pointed to int. We can also operate on values. In this case, the template name is the operation name. The parameters are the arguments, quite similar to the previous case. And the nested member named value is the result. That's the small difference. In order to be able to operate during compile time, we need to declare this data static const or const exp, depending on the standard version we are targeting. Okay, a little example, quite similar to the previous one, but with some differences. So we are trying to increment, oops, sorry, wrong button. Yeah, we are trying to increment v by 1. And here's the example. Yeah, the incrementation happened during compilation. That's the most important thing. Right, so we already can see that something's happening, right? It's already calculated something. So it's already a small program. Yeah, this is our another example. We are going to use it in further examples. We can define a thing called integral constant, and I could describe it as dressing values as types. Types in C++ have many more properties than, let's say, integers. So dressing integers as types might be useful. We can do much more with a type. What we can see here is that, yeah, just as we said, you've got this value member. Also for convenience, we use this. And in line number 14 and 15, we can see numbers 1 and 2 dressed as types. Right? We can type def it, and yeah, keep it for everyone to use. Simple processing. So in order to process something, in order to make our metaprogram alive, we use pattern matching. And we use partial template specialization for that. Let's see an example. Yeah, let's define an if. Pretty useful, isn't it? A basic building block. We can see two templates here. The primary template in line number 1 and a partially specialized template in line number 11. The difference is that the second template is more specific, so it's going to catch all instantiations in which the condition is equal to false, and then the result is the false type. In all other cases, we are going to return the true type. So it works like an if. Right? We provide it with a condition and both cases, and then it selects the right the right type based on the condition. And here's the usage example. Well, we are trying to choose the smallest type which fits some constant. Right? So, yeah, let's say that we've got a configuration file. It defines an integer, and we are trying to use the smallest type for that particular case. We want this code to adapt itself to this given constant. In case somebody changes the constant in the configuration file, we want that change to propagate to all other places of usage. So first we check if that constant is small enough to fit in an int. If yes, then we choose that type. If not, then we choose something bigger. And then we can use it, right? Another case, we want to choose an optimal algorithm for our case. Usually we have to choose between speed or space usage. We could do a similar thing with a preprocessor or with the build system, but this example shows how to do it with a metaprogram. Yeah, in a similar way, we've got a configuration variable coming from somewhere, and we've got those two algorithms. One of them is fast, the second one is small. And we choose one of them based on the configuration. What's the benefit? The benefit is that we keep both of those algorithms alive. This is not dead code, at least to some point. Both of them are being compiled all the time. If we chose one of them with a build system, then probably the other part would not be compiled in a particular case. Right? In this case, both of them are constantly being compiled. And we are staying in C++, so yeah, we can do further processing on those results. Okay, let's show some recursion. In a similar way, we use pattern matching to check that our recursion has ended. And in a similar way, we use partial specialization to define those patterns. Sorry for the little typo. Oh, sorry, here. Okay, a little bit bigger. We can see 4 parts of code. The first template is defined in line number 1, the second one in line number 6, then line number 11, and then usage in line number 16, 17, and 18. Right? So perhaps we could try tracking what this program does. Let's take the first example from line number 16. So we provide the metafunction with an std string, right? And that matches the template from line number 1. And we can see that the rank, so yeah, the amount of dimensions in a provided type is 0, right? And that's also the terminal case. Once the type is no longer an array, that template comes into action and it contributes with this nice number 0. Okay, let's try with line number 17. Here we can see that we feed it with a 2-dimensional array of ints. Okay, so first, let's look at this thing. It is being caught by the specialization from line number 6. We can see 2 things here. The first thing is that, well, the template wrong button. The template automatically strips this 1 dimension, so the type number t has a dimension smaller by 1 than the original, right, type provided here. And then we continue with the recursion, right? So we call it as long as we reach something that is no longer an array. So, yeah, the first, let's say, call, the first iteration happens for the second dimension, right? Then our t is equal to an array, 1-dimensional array of ints, and then we feed it to this piece of code, right? It again catches this specialization, right? And now our t is equal to int, right? We also feed it again, but since int is not an array, we catch the primary template. And if you count it correctly, then it's going to add this little 1 as many times as we called any of those specializations. Right? So in this case, it's equal to. We also have to handle some exotic cases, so like arrays without defined type. The situation here is quite similar, except that, well, these little brackets are being caught initially by this specialization. Right? So pay attention to those details. in case you write your own metaprograms, just to handle all the cases. Okay. So metafunction forwarding is a technique which is widely used. It's used for composing metaprograms, and the benefits are that, apart from less typing, we also inherit all the conventions and all the properties. Let's have a look at the code. Do you remember this integral constant entity we defined before? We can go one step further and define it for a Boolean type and define two cases, like the true type and the false type. And as you can see, we use inheritance so that all of those members in the integral constant are automatically propagated to false type and true type. And both of those types, true type and false type, are distinct types, so we define something new. Right? These are no longer, they are both integral constant, but they are more specific than an integral constant. Pretty useful. And that's the way you create one metafunction from another one if you want to create a specific case. Okay, some other examples of metafunction forwarding. We want to create a trait which says if given type has a size of 1 byte. Right? So we also use the little if we defined before. First we check if the size is equal to 1. As you can see, that can be calculated during compilation type. And if yes, then we choose the true type. Otherwise, we choose the false type. And all of this magic makes it propagate to this. Right? And just as you can see, it has the internal value member, just like defined down to the integral constant, which is the root of all of those metafunctions. Here's another technique, which is widely used, lazy evaluation. Basically, I hope there are no children in this room, so that they don't treat this too seriously, not in life. Well, if you can stay lazy, please do. So, lazy evaluation gives you more flexibility, simply because all of those branches of code which are not being used still compile. We'll show it in a second. And also the compilation speed is much better. Okay, here are the two examples. Okay, line number 2, line number 11. The first case is eager, the second case is greedy. Can you see the difference? Well, the difference is that we extract the inner thing from take it. Okay, let's describe what the thing does. So basically, we want to decide if the type T is our favorite one. And we also defined two metafunctions, or even three metafunctions. The first one recognizes if the type is good enough, right? If we like it. And the second one, takes something from the type T, right? Something interesting, like a little pearl in the oyster, right? And as you can see, in the first case, we extract the inner type immediately. In the second case, we don't do it. We do it at the end. And the property of template instantiation is that, well, if you write something like this, right, the compiler just forwards it down to the template chain. But if you do something like this, it has to evaluate both this and this, right? And, well, the consequences are that first, we use some compilation time for evaluation. And the second, even more useful thing is that, well, both take it and fix it need to be valid for given type T. That doesn't necessarily have to be the case. Let's say that we like the type T because it has some properties inside, and then we want to take it. Well, otherwise we don't want to take it. We don't even want to touch it because it wouldn't compile, right? And in this case, the second example will compile because this is not being evaluated. In this case, both of those branches are always evaluated. Okay, so we can use whatever the language gives us. So all the compile time operators can be used, like size of text type, align of, and so on. And we can use language rules like resolution or conversion rules. Substitution failure is not an error, variadic templates, and so on. Let's give an example. Okay, in this example, we want to check if the provided type has a member function howdy. All right, we want to see if this type has good manners. Like if we say hello to it, it will respond. All right, so let's try using it with three types. The first one is int, primitive. Well, it doesn't have, right? It doesn't have any member functions, so certainly it doesn't have howdy. We've got our neighbor Romek, well-behaved guy. He always says hello to us, right? And we've got a man in black. Well, who knows? Well, a little bit scary to ask, or even, terrifying to say hello to him. And we want to implement has howdy right now. How to do it? Okay, let's give one possible implementation. Intentionally, this implementation is kept in the C++ 03 standard. We'll show something that can be done in C++ 11. Okay, here is our metafunction, right? We want it to be based on an integral constant, returning bool, right? So it's either true or false. And now the whole trick kicks in. Basically, we cannot directly ask if a type has something inside because, well, at least in half of the cases, it might not compile, right? If our given type doesn't have the member function, and if we try to access it directly, well, it would crash. And therefore, we use one more level of indirection and a couple of C++ mechanisms to come up with a solution. Okay, let's try to split this example to pieces. We use helper functions. All right, let's try to forget about line numbers 1 and 4 for a second, so we can see that has howdy function from line number 2 takes an int and returns a car, right? And the function from line number 5 takes anything and returns long, right? So car and long differ in size, and that's what we use for recognizing which function matches something else, right? And that's what we do here. Oh, sorry, wrong button. That's what we do here, right? We check the size of the returned type to check which function is the best match. You can also see that, well, has howdy from int is more specific than has howdy from anything, right? So it has a higher priority when we call it with an int, right? So we try to call it with an int, and now all the magic kicks in. We force this type here, right? We explicitly want has howdy from our type T. Remember, type T is something that we want to inspect. Right? We check if it has this member function. And yeah, I was trying to avoid it, but we have to do it. Lines number 1 and lines number 4. Here's where all the trick happens. Both of them take our recognized type, but here's the magic. We've got a default parameter which matches the signature. Right? So howdy is a member function of type T. Right? We also put some restrictions here, right? That it returns void, just like here, right? And it takes no arguments, so that's a little restriction, probably useful in most cases. And, well, here's what happens. We try to call it with an int. And if all this is valid code, then the most specific function gets called, right? Has howdy from int. This is a perfectly valid code because, well, type T is equal to, let's say, neighbor Romek, and the second parameter is also valid because neighbor Romek has howdy, right? So it's perfectly valid code, and this function is also more specific than this one. So, well, this one is the perfect match. So the size of this expression is equal to size of car, right? And that's how we can recognize that, well, this is valid code. In all other cases, we fall back to the function from number 4, right? And then we return long, and this whole expression becomes false, right? So we somehow indirectly recognized using substitution failure is not an error. Yeah, that's the thing. That our inspected type has some properties. So once again, to summarize, we use this whole trickery because if we wanted to check something directly, it wouldn't compile, so we resort to some indirect mechanism to check it. Right? Okay, there's a second implementation, second possible one. This one requires C++11. Yeah, quite similar, except that it's a little bit shorter. Here, we directly inherit from either true type or false type. So we've got it already packaged. And we provide the function with a null pointer, which can be assigned to anything that's a pointer. Remember that this also gives us some pointer type, right? So if this expression is valid in this context, then we get the true type. Otherwise, we fall back to the less specific case, and we get the false type. Pretty neat, isn't it? Okay, there are a few things which I would love to talk about, but we are time constrained. So we've got metafunction classes, which are the first step to passing metafunctions around. Yeah, please read about it, very interesting. I'm not going to talk about it because it's particularly hard to implement by hand, and at the same time we've got something already made in any metaprogramming library. We'll show that in a second. Yeah, I'm not going to talk about higher order metafunctions, which are composed metafunctions, right? So you can stick things together to create something more advanced. Well, I'm not going to talk about tag-based dispatch, but we had some lectures about it, so yesterday you could get a taste of this technique. Basically, we add a second level of abstraction so that we can process groups of data in a similar manner, right? And I'm not going to talk about periodic template parameter pack access. That's also very useful, at least once you start metaprogramming for good. Please look it up, very useful. Okay, once you start writing some metaprogram code, you'll notice that it's quite easy to abuse it. Yeah, and we still have no concepts in C++, so we have to resort to some other mechanisms. One of them is usage of static assert with some traits like std is same or alike. We'll show it in a second. Also testing, right? You can test your metaprogram in a regular CPP file, right? The one that sits with your code, and it has. And if you compile that file with your code, you gain early and frequent testing. Right? That's one of the things you always want to achieve: testing as frequently as possible and as early as possible. And you cannot be more frequent and more early than doing it during compilation phase, right, of the code. Okay, so here's an example. Okay, we have a metafunction pass optimally. Probably you wouldn't want to implement something like that yourself because it's already present in Boost, but here we have it for demonstrational purposes. Yeah, so we check if trying to pass a class yields a reference while passing a built-in type yields a value, right? And we can use it. We can use static assertions. We can use is same. Then we get a very nice message. What got wrong, right? And these are two test cases of our metaprogram. We can write as many as we want to. Yeah, here's an example of assertive code. Yeah, so this code is interfacing some computed types, right? The ones that we computed with a metaprogram. So we want to, and it also can be touched by the user, right? So we want to check both if our metaprogram is okay and that the user doesn't want to do something illegal, right? So we basically check if all of those types which we fed into a function match each other, and before we use all of them, we have a static assertion. So the error message is probably going to be much more user-friendly than as if we omitted this static assertion, because then we would get a compiler message, right? Not exactly saying directly what got wrong. Okay, so let's demonstrate STL in C++11. We got a very useful sublibrary named type traits, and it's a basic thing when you start metaprogramming, right? So it provides you with means for type introspection, like is integral, is pointer, is function, and so on. Many of them. We can also do some basic type processing, right? So we can modify types, and we've got some basic metaprogramming facilities, like the conditional, which is a nickname for if we showed just a second ago. We've got the integral constant, like enable if, result of, and so on. Let's show it. Let's show what a typical program with type traits looks like. All right, so what we are trying to do here is writing a function, always positive, which returns the absolute value of its argument. So let's have a look at line number 7, right? And we also want to mingle with the type. So if we know that the number is always unsigned, then we can encode it with an unsigned integer, right? And that's what we are trying to achieve, right? So what is happening here is that for unsigned types, right, we always know that they are positive, so we can return them as they are. What is going on here? Well, we use substitution failure. It's not an error here, right? Have a look at enable if. What it does is taking a condition and either forwarding the type t to its result or not, right? If the condition is false, then the type t is not present. And that makes this code invalid. And the whole thing will not compile. And that's what we are utilizing here, right? So if the type t we are providing here is unsigned, then this code is valid, this code is not, right? So this is being cut away by the compiler, and we get this version. Have a look that this is some kind of generalization of function overloading. Right? We can use a metaprogram to, well, define our own overloads for the whole families of functions, and that's pretty powerful. And in this case, as you can see, right, those two cases are mutually exclusive. That's pretty important. Otherwise, we would have conflicts during compilation. What we do here is making the type unsigned, right? Then, well, calculating the absolute value and then returning it, right? We utilize the automatic conversion rules. What we gained here, well, the first thing is that this code is shorter than this one, so it's going to be faster. And we gained some elastic processing. Well, this is a trivial case, but perhaps we want to make exceptions for whole families of types and then process them in some unique way. Okay, let's talk about BoostMPL. BoostMPL is a full-fledged metaprogramming library, and what it does is mimicking STL in such features as containers and views. So we've got a vector, a list, a map, algorithms for processing, and some utilities. The difference is that STL operates during runtime. MPL does a similar thing during compilation phase. So let's have a look at a sample program. Okay, we are trying to implement a poor man's tuple. How can we do that? Right? We want to feed the tuple with a list of some types, right? And then we want to access it by type. Right? So in line number 2, we want to get the int part, right? And in line number 3, we want to get the char const. Yeah, the string part, right? The C string part. Yeah, let's try to do this. So first, in line number 6, we defined a basic bit of a tuple, which takes the type T and creates a member with that type. Right? We also define the accessor. What is going on here is, implicit casting. And we'll have a look how it works in a second, in this particular second. So, what is going on here? Well, of course, we have to include all the headers, and then we are trying to express our tuple by inheriting over and over those little bits we defined before, right? So we want to inherit the tuple field over and over with different types, and this will cause, well, all of those fields to accumulate in that result type. And that's exactly what is going on here, right? So we take the list of types, and then we fold them, right? But not in an easy way. Fold is something like accumulation, right? So first we create a collection with those fields. Our starting point is an empty base, so something empty, we don't need it. And then we provide an operation which is being done over and over with each fold step, right? And in this case, it's inheriting. So, you probably noticed those two little signs here. These are the placeholders, which means that, okay, take my vector, take my first initial element, and feed it here, right? And take the second one, and feed it here, right? So in this case, we have and inherit one from another, right? So we take an empty base, then we add the tuple field from int, and then we do it for all the other elements of a vector. You see that looks like a classical algorithm in STL, except that it happens during compilation time, and the result is the type. And Boost HANA, that's the new child of the Boost family. It's a successor to both MPL and Boost Fusion, which means that it's able to both aid us with compile time computations, runtime computations, and heterogeneous computations. So that's something that crosses the boundary between runtime and compile time. Well, we also have to pay for it. We need a decent C++14 compiler. So let's have a look what a sample code in Boost HANA looks like. So this is going to be a heterogeneous operation. We want to, first we define some types. Right? This is going to be our data. Then we create a collection. Right? As you can see, our data has a name. Right? All of those three types are different, but this member is the same. Right? So, well, we can run an algorithm on such collection, returning that name. Right? So we are sort of iterating and transforming a collection of different types. As you can see, this is a runtime computation, and the result is also a runtime collection. Right? We can see that we extracted the names of those cute animals. Okay, that's a second example. And what's fascinating is that it looks almost exactly the same as a runtime version. Right? We also create a collection, but you can see that it's a collection of types. It's not a collection of instances. Right? And we can also run an algorithm in a pretty similar manner, and then check the whole thing in the compilation time. Right? So the fascinating thing is that both runtime and compile time computations look the same in HANA. Right? So we can freely cross the boundary between runtime and compile time. That's pretty cool. Okay, thank you. Questions?
Okay, so what is difference between const exp function and metaprogramming? Because in both cases you use computation at compile time, yes? So what is the difference?
Okay, so I would say that C++ keeps on evolving, and it keeps on offering us features which were not present before, and those features will tend to overlap in some way, right? A const exp function intimately yields us a value, right? It doesn't operate on types, right? So probably metaprogramming is a slightly broader term. It can do much more than just a const exp function. And of course, you can employ const exp function in your metaprogramming journeys.
Hello. You made an example about checking if the type contains it was a howdy method. I think.
Member function, yes.
Yes, and this way of checking this is basically a hack, right? It's you are checking this by checking something else, and if someone would read this code, wouldn't possibly understand on the first sight what does it do. But I understand it does the job if it is needed. But would you recommend using such solutions in actual production code?
Okay, let's switch to that example. Not yet. Okay, so as you can see, we are trying to hide all this hackery with a pretty standard metafunction. As you can see, the user sees a regular metafunction, doesn't have to, look under the hood. Yeah, that's what we said. We are shifting complexity under the hood. So the user sees something nice and shiny, and it doesn't necessarily have to be that simple under the hood. Yeah.
But the fellow programmer who sees also your solution and someone might see this.
Yeah, I would. Yeah. I guess the best recommendation is to simply document that code.
Okay.
Probably.
Thank
I
you.
mean, that's a pretty standard pattern, right? That you use a helper function to recognize something that would otherwise not compile. So somebody at least moderately proficient in metaprogramming would probably recognize it as a pattern. For the other people, you have to document it.
I just like to comment that it's not really black magic. These are some difficult tricks, but if you just want to give someone a pretty neat functions, you don't have to look under the hood.
Oh, I like this question. Please ask more questions like this.
Excuse me. Does it work? Can you hear me?
Oh, yeah.
You showed us this HADA library. Is there a standard way to tell which computations were processed on the compile time and which computations were processed at the runtime?
No.
Because you showed us two examples. One of them was done at runtime, one of them was made at compile time. Is there a way to tell which one were done when?
Yeah, probably by reading the code. Simply we create some instances here, right? We create a tuple, and the library hides all the details, right? Here we feed it with, okay, this is something wrapped, but this is generally a type. Right, so you simply have to read the code.
I may answer this question. Boost HANA provides asserts. Boost HANA provides asserts, runtime assert, const exp assert, and static assert. So Boost HANA provides asserts that you can use and check.
Thank you.
Yeah, thank you. Thank you very much.
Didn't mean the project that provides metaprogramming, but to do something, maybe some codecs, some user interface, anything that users want, not programmers?
Tough question. Do you guys know any really big libraries? Well, I guess perhaps not using this convention, but certainly Google Test and Google Mocks uses lots of metaprogramming under the hood. Yeah, that's what enables users to use such a neat interface, right? Plenty of stuff is being hidden.
Hello. May I have a question? About this MPL, I do see why trades are useful, but can you say one or two projects where you seriously used MPL HANA and I didn't saw any other way to do it properly?
Okay, so I have to admit, I haven't used...
Awesome. Written wise and read many times, as you can hear on other lectures here. And reading or debugging, well, MPL or HANA is not the easiest stuff. So can you say when you in practice used it? Not
agreed.
Hobby one or...
Okay, so I haven't used HANA anywhere except some pet projects, so let's say some small examples. It's a pretty new stuff. But I used MPL. Well, in most of my career, I worked on commercial projects, so I used it there. And well, just to give you an example, for example, we had a very huge device with thousands of registers, and each register had several bit fields, and all that was described in a Microsoft Word document, right? And we had an option, either to handcraft the code, right, to create some accessors and mutators for those registers. We were implementing something like a device driver, or use a metaprogram. So we managed to do something like extracting the documentation, of course grabbing it a little bit, and then feeding it directly to a metaprogram so that it generated a map of this device so that we could access it just as it would be, well, using names similar than those used in documentation. Right? So that project required lots of typing, but thanks to a metaprogram, we could do it semi-automatically. Right? Of course, yeah, there's a trade-off. Yeah, I guess I'm trying to grasp what you meant. Yes, metaprograms might be not easy to read. They definitely require some skill. But just as I said, you are shifting some complexity from the code which you would otherwise have to write manually to a library or a utility, which encapsulates that. And very often, if your business logic is more sophisticated than your utility, then the benefits are going to be quite huge. And I admit, once you take the metaprogramming path, it might be quite hard to go back.
So maybe one comment to your question. There is actually going to be a talk by Odin on session 2, actually. So the next one, Modern Embedded APIs. And actually Odin will be talking a lot about the usage of metaprogramming for abstracting registers for microcontrollers. So actually this is like very practical application, and basically it allows you to generate a code that is faster than like handwritten C code that people usually do, and it's like much faster. So I think this could be interesting to you to answer the question.
Okay, guess we are done. Thank you so much.